Let's now use that method of images and consider what happens if we have a point charge above a grounded conducting plane. So I've got the simple system drawn here. We've got some positive q, which is some distance, let's call this distance h, above our grounded conducting plane. So of course in that conductor we have zero electric field and zero potential. And let's also say that this is our positive z direction, so it's going upward on the page. So using our method of images, we know that we can replace this system by that charge configuration, some equipotential surface, and in this case that's going to be v equals 0. So let's go ahead and draw our equipotential surface. So this is going to be v equals 0, and let's put our original charge up here, and then equidistant from that in sort of below our equipotential surface, we're going to have our image charge, which in this case is going to be negative q. And so we're not going to go into sort of a lot of the details, but if we were to draw our electric field lines, what that would look like is we would have something that looks like this for our q. So remember, our electric field lines are going to have to be perpendicular as they come into or leave a conductor. So we get something like this. And so those arrows should of course be touching the conductor. And then once we're in our image, we could have, or once we're sort of on the image side, we would have something that looks like this, continue into this negative q. So those would be our electric field lines. So let's go ahead and just write that here. These are our field lines. Now, let's say, for instance, ultimately what we wanted to know is, based on this initial configuration, we wanted to know let me move this out of the way. So we want to know our electric field at some arbitrary point outside of the conductor. So this is some arbitrary point at x, y, z. Again, keeping in mind that anywhere inside our conductor, we're going to have our electric field is equal to 0. So the easiest way to do that is to come down here to our model with our image. And so we can say P of x, y, z is right here. And we're going to consider the effect from both of those point charges. So we can say, let's find E at P using our equations for our point charges that we looked at back when we started talking about electrostatics. So of course, if we're going to do that, we know we're going to need some distance vectors. So let me go ahead and draw in some distance vectors here. So we're going to need a distance vector from our q plus, and we're going to need a distance vector from our q minus. So we get something that looks like that. And so let's call this one up here to be consistent with the notes r1, and this distance vector r2. All right, so now that we have those defined, we can come down here and say that our total electric field is of course going to be the sum of the electric field from the 2 point charges, so from the positive point charge, and our electric field from the negative point charge. And so those equations are both going to have the same form. So for the positive point charge, we're going to have the charge, which is q, not our position vector, but our distance vector between the two, which is going to be r1, divided by 4 pi epsilon. In the notes have epsilon naught, but to be more general, we can just say epsilon r1 cubed. Similar structure for our E minus, except now we have a negative q because we have a negative image charge. Our distance vector is r2. We're still dividing by 4 pi epsilon, and now we have r2 cubed. And so of course if we plug in, of course we said we know this distance from from q plus to our surface is h. So that means that this distance is also going to be h from our image charge to our surface. So we could then talk a little bit more about what our r1 and r2 are. So our r1 is going to be our point P, which is x, y, z, minus the place where our q, our positive charge is, which is, let's just say 0, 0, h. We can define our x and y as whatever we want because we weren't specifically told it was some x and y. So we can kind of move our coordinate system to fit our needs. And so we get that this r1 vector is x, y, z minus h. Similarly, we can say that our r2 vector is going to be that point, or our position vector for P, which is x, y, z, minus our position vector for our negative point charge, which is 0, 0, negative h. So similar form here, x, y, and now we just have z plus h. So once we have that electric field equation, of course we could plug that in for our R1 and R3, or sorry, R1 and R2 above. We could then go on to find other things. So for instance, if we wanted to find our voltage outside of the conductor, so of course we could find our V inside the conductor is just 0. So if we want to find V outside of the conductor, well, one method would be, of course, we could go back to our basic electrostatics, and we actually had equations similar to these for our electric potential. So we could do that, but we don't necessarily want to redo that work because we've already done it for our electric field. So we could go back to our previous unit's equation, and we could say that our voltage is equal to negative line integral of E dot dl. Now remember, of course, with voltage, we need to be talking about potential between 2 points, so that's why we have an integral over a line. So that could be one item of interest. Let's say we're also interested in our surface charge density. So how much charge, if we come back to our initial system, how much charge is induced on this conductor surface as this, well, let's put that back, as that positive Q is approaching the conductor. And so we can find that value by saying our rho s is equal to dN. And again, that's something we considered when we looked at our dielectric conductor interface. And we know our dN is going to be epsilon naught En, and that's going to be evaluated at z equals 0. So essentially we're looking at this case here where we're right at the interface, because that's where we know our electric field is going to be normal. So we could find that rho s. Now, if we ultimately want to find the total charge induced on the conducting plane, so let's say we want total charge induced on our conducting plane. So we're not going to go through the details of it, but basically we could sort of follow this path. Once we have our electric field expression, we could find our rho s, and then ultimately we could say the total charge induced is equal to the surface integral of rho s ds. And so if you want to see some of the background work as to how this works out, you can look on pages 268 and 269 in the textbook. But basically we're using, of course the form is going to more or less look like this. And then we're playing some games to get these sort of variables into a nicer form for integration. And so when we go through that whole process, we end up finding that the surface charge induced is actually just negative Q. So we had positive Q coming towards the surface, and we induced some surface charge of negative Q. So this was a relatively simple case where we just had one conductor and one charge approaching. As you might imagine, things get more complicated as we have multiple conductors involved or multiple charges in our charge system. So if you want to get sort of a better feel for that, there are a couple examples with some more complicated arrangements in the textbook.